Okay, so question 2 is the carbonyl question, aldehydes and ketones. First thing you have to do is to name this ketone. So 6 carbons, no carbon-carbon double bonds, so hexane, and if this is carbon 1, 2, 3, hexane 3 lone, and carbon 4 then has got the methyl group, so 4 methyl, hexane 3 lone. Now it says, suppose this is a wonder drug for treating this nasty disease. Why might it be advantageous to get it from a natural source, like ants, rather than make it in the lab? Whenever it asks about what's the good thing about natural products compared to laboratory ones, it's not usually something trivial like cost, it's usually about chiral centres. And if you look at this compound, you can see that it does indeed have a chiral centre there. Okay, because you've got methyl, ethyl, this lot, and then hydrogen for the 4th one, so 4 different things around it. So what you should say is, first of all, that it has a chiral centre and therefore can exist as a pair of optical isomers. Next point you have to make is that when you have that situation, usually only one of the optical isomers is actually active as a drug. So the advantage of giving just that isomer is that you need a lower dose, because you're not giving half of the stuff that won't work, so you need a lower dose, and you avoid the possibility that the other isomer may have harmful side effects. Okay, so advantage would be if you could give the single isomer, need a lower dose, avoid the risk of harmful side effects from the other isomer. And that brings us round to the ants then, because if the ants produce just the product that we want, and the point is that living systems tend to just produce one optical isomer, because the enzymes that make the compound are themselves chiral, they favour production of one isomer rather than the other. So if the ants just produce the isomer we want, then we would avoid the problem of having to do a chiral synthesis in the lab or having to separate the isomers from each other. So it just wanted you to recognise that natural products, where there's an optical isomer, you typically only get one of them. Okay, so lots of points to make there. Now it's asking you about reduction. So you can reduce this with sodium tetrahydridoborate. You need to recognise that name, although normally you could just call it NaBH4, which is easier. But in the equation, remember you just use the magic hydrogen to represent the reducing agent. So it's that plus 2 moles of magic hydrogen from the reducing agent will give you the product, and all that happens is that that ketone group becomes reduced to a tertiary alcohol, secondary alcohol. Okay, so the ketone group is reduced to a secondary alcohol like that, and that's it, that's the whole equation. You need to know a lot about that reaction because it's the set piece mechanism that you have to learn. Using H- as a nucleophile, it's the paradigm for nucleophilic addition. And that's what the next question is about. That's saying, okay, if you've learned the mechanism of that one, you should be able to cobble together a mechanism for a different nucleophilic addition. In this case, addition of a phenyl anion, C6H5-. So what that is benzene, except that instead of one of the hydrogens being there, you just have a lone pair of electrons, and that gives the whole thing a negative charge. Okay, so this is the, let's get rid of this lot. This is where you're starting, and the point is that because this is negatively charged, and it's got a lone pair of electrons there, it can act as a nucleophile. And what it will be attracted to is the dipole in this compound. So you need to mark that on, delta plus, delta minus, like that. And then remember the lone pair of electrons makes an attack on the delta positive carbon, so you get that. And at the same time, because the carbon can only form 4 bonds, the pi bond here has to break, and you get that as well. So 2 lone pairs of electrons have to go on there. 2 curly arrows have to go on there. And the second one generates a lone pair of electrons, which appears there in the intermediate. Okay, so this is the next phase. We've now only got a single bond there, and O- at the top, and the phenyl group has now been attached, like that. In the second phase of the reaction, you add water, and that's important because this O- has got to grab a proton from somewhere to generate OH, and so it does that, and again you can do the curly arrow to show it. So there's the curly arrow from the lone pair, which it's using to pick up H plus from there, and if that picks up H plus, these electrons will move out onto that oxygen to create OH minus. So your final product is that tertiary alcohol plus OH minus with its new lone pair like that. And that's the mechanism. So again, learn the tetrahydroborate mechanism with H minus first, and then see that this is basically the same, just with a different nucleophile. Final thing it asks you is, if you do that reaction, how you could monitor the progress of it using infrared. That's simply to say that the carbonyl peak, C double bond O, remember to quote the wave numbers, 1640 to 1750, that peak would get smaller as the ketone is used up, and at the end of the reaction it would have disappeared completely, so it gives you a convenient way to monitor the reaction. Okay, that's it for question 2. How'd you turn this thing off? Oh.